Yeah, maybe quick introduction to myself. So as said, I'm Marco Karer. I work with the Vision for Robotics Lab under the supervision of Margarita Klee, and essentially my research topic is on visual SLAM in general, more specifically on the collaborative aspect where we try to perform SLAM with multiple agents. So with that, I would directly jump into my presentation, which is basically about how we can utilize collaboration for an accurate and robust state estimation. So as one knows, or most of you knows, that SLAM constitutes a core building blocks toward providing robots with the navigational autonomy. For example, in this video, we can see some footage of a commercial drone, which is designed to capture sports and action movies. So this product essentially uses cameras and inertial sensors to perform SLAM and navigate within its environment. Obviously, the drone has also a whole bunch of other technology. But the bottom line is essentially that single agent VI SLAM already has reached the maturity and robustness to be deployed in commercial products. On the other hand, for many applications, we would like to deploy teams of robots to essentially augment each other's capabilities. But the perception abilities for such multi-agent systems, unfortunately, are still far from their single-agent counterparts. Nonetheless, the capability of multiple robots to perform SLAM can provide the team with a common reference frame, which in return allows the coordination between them. But from a perception point of view, collaboration essentially can provide more than just a common reference frame. For example, reusing each other's information can help to reduce the drift in motion estimation on board of the individual agents. So if you're interested in this type of application, I recommend you checking out some of our previous work, where the first one essentially we investigate the backend fusion of visual inertial SLAM data. And the second one, the CVI SLAM, we essentially could demonstrate the first centralized collaborative visual inertial SLAM system, where you could show online reuse of the map. However, in this talk, I will focus a bit more on a tighter form of collaboration between a pairs of agents, essentially forming some sort of a stereo camera. So starting with a traditional stereo camera with a fixed baseline B, the perception of the depth, or essentially the triangulation angle, is okay as long as the camera is close enough to the scene. But as the camera moves away from the scene, the triangulation angle essentially shrinks, and the stereo camera degrades towards a monocular camera. So having such a stereo camera that could adjust the baseline based on the scene requirement could overcome such a limitation. The idea of using, for example, two UAVs as a virtual stereo camera was originally proposed by Achterlich et al., where a loosely coupled filter approach was proposed, fusing IMU and visual information to estimate essentially the relative pose. We extended this idea by fusing odometry and visual information in a tightly coupled fashion in our ICRA paper in 2018. While this showed that we can estimate the relative transformation between the agents using their individual odometries, in the end, the estimate of the baseline can only be as good as the individual agents' odometries themselves. Driven by this insight, we thought, why not include a simple distance measurement to make essentially the baseline between them directly observable, which in essence constitutes the basic idea of the system I will introduce next. In this system, in the system, essentially the UAVs are equipped with a camera and the IMU each. And additionally, in order to metrically constrain the baseline, we also add ultra-wideband module, or short UWB, on board of each agent. Using a time of flight principles, these are able to measure the relative distance across the agents. Now, all of this sensor data gets fused on board each agent's own estimator. Now, besides the exchange of some keyframe data, the estimators also communicate some sort of a consensus variable in order to arrive both at the same estimate. So let's now have a look how these onboard estimators are built up. And in essence, at the heart of it lies the visual bundle adjustment backend using the relative distance measurements which builds essentially a graph as follows. So first we have our keyframes from agent A shown in blue, and the ones from agent B shown in red. These keyframes observe a set of map points, where the ones observed only by one agent are indicated in the corresponding color, and shared map points essentially are shown in purple. And further, and the main part, we have also a set of relative distance measurements, which in general are at a much higher rate than the keyframes themselves. For example, in the order of 50 Hertz. Now, in order to fuse this distance measurement with the visual observations, we propose to make use of a spline-based interpolation. Such an interpolation enables us to compute a 6-degree of freedom pulse at any time point between the existing keyframes, essentially allowing to incorporate the raw distance measurements into the optimization. Now, before I go deeper into how we optimize this graph, let's for a moment assume that we have access to an optimized version of this graph and have a look how we generate the correspondences and also how we estimate the actual frame-wise pose in our system. Except from assuming we have a set of optimized map points which are expressed in some map frame. Now, in addition, in the system, we maintain a rough estimate of the corresponding uncertainty for every map point. Now, as we would like to make use of the IMU in our tracking in order to obtain a smooth estimate as well as a robust performance, even for the presence of sudden motion, we need to be aware of the gravity direction. Further, we include the IMU related variables, namely the velocity, IMU bias variables in our state. And finally, of course, the actual goal of the filter is to incorporate the camera state or camera pose itself. Now, as the map points themselves are not actually part of the filter state, we utilize their approximated uncertainty instead in the following way. So first, we have our feature detection uncertainty in the image plane, which is shown here in blue. And then further, we actually project this map point uncertainty itself onto the image plane as indicated here in gray. And now if we add essentially these two uncertainties up, we get some kind of an inflated measurement uncertainty indicated here in green. This inflated uncertainty is then in return used to incorporate the map point observations in our tracking EKF. Now for the estimation of this map point uncertainty, we essentially make an independent EKF per map point and perform more or less the inverse operations using the estimated pose uncertainty. Now this procedure is certainly not consistent in terms of their uncertainties, but in our case, really the focus was on getting a simple IMU integration to obtain a smooth and robust performance in terms of fast motions. Now let's come back to the graph representation that was used in the backend. So essentially, the estimated frame poses will get used as an initial guess for the keyframes, where in our case we selected a time-based keyframe selection criteria, which is simply motivated by the fact that it's easy, but also by the fact that we use the keyframes directly as a base nodes in the interpolation. Now, in order to generate new map points, we utilize the heuristic for the candidate selection based on the keyframe viewpoints, baselines, plus we also add some bias towards favoring cross-agent triangulation over intra-agent triangulation. As we have seen for the tracking, each agent requires to have access to an optimized map. But since the agents do not have access to a shared memory location, how can we actually optimize the individual graphs in a consistent fashion? Now, to do so, we utilize a distributed optimization scheme, which I will introduce now. For that purpose, I will use a traditional bundle adjustment problem as an example. Let's assume for the problem has 4 participants, which all share some observation with the neighbors. Now, the overall problem can be written as the sum of some error function f, which in this case would be the squared, essentially the squared reprojection error. Now, in order to distribute the problem, we cut the graph to the shared variables and divide it into 4 parts. We can now build up 4 subproblems, including a copy of the corresponding shared map points in every subproblem. Now, if these subproblems were independent, we could just solve the following in parallel, where phi k essentially just represents the summarization of the corresponding residuals in subproblem k. Now, if you would do so, we would most certainly not arrive at the same solution as to the original graph problem. But if we now add some constraints on the shared variables, essentially in this case the marked map points to be equal across the subproblems, we arrive at an equivalent formulation to the original problem. These matrices S here simply denote selectors, essentially to select the shared variables out of the subproblems. Now, to solve this constraint problem, we utilize the AROC algorithm, which was introduced by Peng et al. For this, essentially for every shared variable between 2 subproblems, a dual variable set is introduced. The variable nk denotes the set of subproblems which are connected to node k. Now, in a nutshell, this means, in this case, for every shared map point on every node, one dual variable per shared observer is introduced, which in this concrete example is 1, as every shared map point is only observed in 2 subproblems. Now, for the actual solving of the overall problem, the subproblems get essentially extended with an additional error term. Now, this term in essence punishes deviations between the local copies of the shared variables and the consensus with the neighbors. Now, after each minimization, the dual variables get updated using the latest received information from the neighbors, which is indicated here in red. The updated dual variables itself then in return get communicated to the neighbors back. The variable nu in the formula here is responsible to allow the received dual variables to be outdated, which essentially allows for asynchronous solving and also for some delays in the communication. Gamma is simply a parameter to determine how much emphasis is given on the consensus. Now, these 2 steps essentially are iterated and repeated over time. Now, coming back to the original problem setup when using the relative distance measurements. As one can see, splitting the problem to the shared map points would be problematic, as all poses are connected to ultra-wideband measurements. Now, instead, we propose to build up the complete graph on each agent individually and use the decentralized optimization scheme in order to achieve consistency across the agents. Now, in order to avoid the exhaustive and complicated bookkeeping, we only enforce the equality constraints across the keyframes. But the map points are generated on each agent independently, and we do not enforce constraints on them, meaning that they are allowed to be different on both agents. Now, in order to test our algorithm safely, we use the VI sensor simulated pipeline as proposed by the Scher et al., which, by the way, is available open source on our GitHub page. Essentially, it uses the Rotor S framework to simulate the UAV dynamics and generate IMU measurements of the sensor. The rendering data of the image data is built around the Blender rendering software, which gets fed with the ground truth poses and some photorealistic 3D models. The ultra-wideband information was generated simply by disturbing the ground truth distance between the UAVs with some Gaussian noise. Now, in the first experiment aimed at investigating the limits of classical single-agent stereo inertial methods at high altitude flights. To do so, we simulated the UAVs to fly a spiral with increasing height, where we linearly increase the distance between, or the baseline essentially between the UAVs with increasing flight altitude. In this plot here, we can see the comparison between the stereo inertial methods and our approach. Clearly, both stereo inertial methods start to significantly deviate with increasing height, with the main reason being that they struggle to maintain the symmetric scale properly. Now, to investigate this further, we computed the statistics of this scale error at different heights. As one can see, starting at around 30 meters, the scale error for the stereo inertial method becomes significant. On the other hand, as one can expect through the variable baseline as well as the incorporated distance measurement, the scale error for our method remains bounded. Now, in further experiments, we essentially implemented a simple control scheme to automatically adjust this baseline formed by the two UAVs based on the scene. So what we in particular used is essentially the median observed scene depth, which was used then to control the UAVs such that they really form a visual stereo camera with a baseline chosen such that the desired triangulation angle is achieved. Now in this video, we can see the system operating with the adaptive baseline controller active. On the left, we can see the UAV's current images, while in the 3D view, the camera frustrums are illustrated in light gray, and the two agents estimate and map points are shown in green for agent A and pink for agent B. We can see how the baseline gets adapted according to the estimated scene depth. Note that here in this video, for the visualization purposes, the UAVs are shown oversized. We then compared essentially this adaptive approach against simply using a constant baseline throughout. Now, as one can see, a significant reduction in the error could be achieved by choosing an adaptive approach. What this essentially demonstrates is that adapting the baseline upon the scene requirements essentially has a large potential. Now, using the same data, we can also evaluate the consistency of our distributed optimization scheme. If we globally align the trajectory as estimated by agent A and that one estimated by agent B, we get the following errors. If we now align the combined trajectories and compute the combined RMSE, we essentially get the average of the two individuals. Now, what this means is that the estimates themselves are consistent across the agents, which can be shown with the following argument. Because if there were any inconsistencies between the two estimates, meaning that the trajectories do not match across the agents, then the combined error must be significantly higher than the average of the individual errors. In summary, what we presented a novel collaborative sensor fusion framework which fuses visual inertial data along with relative distance measurements. The backend of the system is built on top of an asynchronous consensus-based optimization algorithm, which allows us to deal with potential network delays. Our evaluation revealed that we can achieve a higher accuracy of our estimates at altitudes up to 150 meters. And that by using an active baseline control scheme, we could show a significant improvement in the system's accuracy. While we performed some preliminary tests on the real system, unfortunately, most of the tests so far were carried out in simulation. Now, before I end this presentation, I would like to give some broader context of the applicability of this of the presented optimization scheme, which I presented before. Recently, there has been quite some interest in approaching really large-scale bundle adjustment problems. Now, in order to scale up to really large graphs, methods of parallelization essentially have gained traction. Starting with an initial graph, which can be from a SLAM system or a structure from motion graph, this graph essentially gets then partitioned into smaller subproblems, for example, through graph cut methods. By now, the approach of partitioning large graphs into smaller subproblems should ring some bells. Now, instead of making up for the lack of a shared memory, one can essentially distribute the subproblems on a compute cluster and solve them in parallel. The current approaches, such as the one listed below, so far are built around consensus-based synchronous ADMM methods, which essentially average the results of the worker nodes and send this average back to the workers themselves. Now, for a perfect partition graph, the synchronicity of the algorithm does not really have any negative implications. However, in reality, it's basically impossible to achieve such a splitting of all that all subproblems are of equal size and essentially structure. But this has the consequence that the overall iteration speed is dictated by the slowest worker node, essentially creating some dead times on the faster nodes. By using, for example, the presented asynchronous approach, this dead time could be eliminated and potentially reduce the wall time of the problem by increasing the utilization rate of the worker nodes. However, due to the peer-to-peer structure of the algorithm, its possibilities exceed the use case of optimization of large-scale data and could be also applied to distributed optimization in a decentralized system, such as, for example, a fleet of robots. Here, such a scheme would allow the individual agents to benefit from the global scope, while only storing local information and sharing some parts of this information with its neighbors. With this, I'm at the end of my presentation. And if you're interested, I would like to invite you to have a look at some of our work in our collaborative Visual Slam. While the core of this presentation will also be presented at ICRA next month. With that, I would like to thank you for your attention and feel free to ask some questions.